Okay, today we're going to be solving 2-sum with brute force. This is what the problem looks like, and I've linked the problem in the description. So, in this problem, we're given two inputs. We're given a list of numbers, and we're given a target number. What we want to find is the indices of two numbers in the list that add up to the target number. So in this example, the numbers would be 1 and 4. But how do we program this? In this particular solution, we're going to do so by trying all possible combinations. Let's start at the beginning of the list. We start with 3, and the next number we want to pair with it is 0. That sums to 3, which does not equal 5, so we continue by moving the second number over. So 3 plus 1, and 3 plus 4, 3 plus 6. We see that none of these add up to our target number of 5, and so we move on. We move our first number to the next number. So we start at 0 now. We've already tried 3 with 0, so we don't need to do that again. So instead, we'll start with the number directly after 0, 0 plus 1, 0 plus 4, 0 plus 6. Again, we didn't find the target number, but you can see the pattern of what we're doing now. We start at 1 plus 4, and this does equal our target number of 5. Just to illustrate that this does go through every number, we're going to now do 1 plus 6, and then finally 4 plus 6. If you want to be rigorous about proving that this goes through all combinations, a little math says 5 numbers in our list, choose 2, is equal to 10, which 4 plus 3 plus 2 plus 1 is 10 combinations. We tried them all. Okay, let's write this out in code. So generically what we did was we started at the first number and we tried that number with every number after it. We moved to the second number and continued, third number, etc. So let's try to write that down in code. So for I, the index of the first number in range length of nums, so that goes from 0 all the way to the last index in our given list. But before we do any kind of summation, we need the index of our second number as well. So for j in range, I plus 1, because we want to start at 1 after the first number, all the way down to length of nums. Now we have the indices of both numbers iterating through the entire list. So now we can actually perform our operation of adding them together and then checking whether they equal the sum. So now we do nums of I plus nums of j. We want to check if this is equal to our target. And if it ever is equal to our target, we just want to return these two numbers in the specified format, which in this case is a list of ints. So return I, comma, j. We submit it. And it works. So fortunately, in this specific solution, we don't have to deal with a lot of different edge cases we might normally run into. For example, we don't have a case where there's no solution, in which case we would exit this loop and get to this line here, which we wouldn't return the right thing because we just wouldn't return anything. We also don't have to find all the solutions, which would also be a little more complicated because we would need to keep track of everything that we find instead of just returning the first thing we do find. So in this specific formulation of the problem, we're done. The last thing I want to talk about is time and space complexity. For time complexity, we're given two inputs, nums and target. Target doesn't change in size, it's just a single number. Nums is what will vary in size, so it can grow without bound, and therefore it's our key for figuring out time complexity. We'll call the size of this list n. So going back to our manual example, we see here, let me erase this. Whoops, let me erase this. So we can see here, we first had 4 numbers in the first iteration, then 3, then 2, then 1. More generically, we started at, well, there's 5 numbers in this list. So this was n minus 1, n minus 2, and then we go down all the way to 1. So putting this in math terms, the sum of I equals 1 to n minus 1 of I. I'm going to skip a couple steps, but this equals n minus 1 times n over 2, which is 1/2 n squared minus 1/2 n. And in CS asymptotics, we don't care about a lot of things, and so we just take the largest term without the coefficient, and this is equivalent to O of n squared. For additional space used, aka space complexity, we're only creating variable I and variable j, and we're storing nothing else in our equation. Those two don't grow with the size of nums because they're just single spaces in our stack, and so our space complexity is O of 1. And that's it for brute force 2-sum.